Hi everyone, I'm Junwen from University of Chicago. I'm excited to introduce you our work on synthesizing complex pipeline by target. This is a joint work with Yeye and Surajit from Microsoft Research. Data preparation is extremely important today. Data scientists spend up to 80% of their time to prepare data by building complex data pipelines for data analytics and machine learning. According to Gartner, this is the most time-consuming step and is a multi-billion-dollar market. There are many established tools that help professional data engineers to build data pipelines, and recently, less technical users increasingly need to prepare data themselves. So there is also a new generation of self-service tools. Existing tools allow users to use drag and drop to create data pipelines one step at a time. But then within each step, users are expected to parameterize correctly, such as how to join and what columns to join. This is a lot of work and requires technical experts. We ask an ambitious question here, whether we could automatically synthesize multi-step pipelines end to end, which is what we want to achieve in this work. Our key observation here is that a common usage pattern in pipeline building is to introduce new data files. For example, a large retailer has sales data coming from stores in different places and across different time periods. For some version of the input, a data pipeline has been manually built previously that populates a database table or a BI dashboard. However, as is often the case, new chunks of the data will come and their schemas and formats often have evolved. Obviously, building a new pipeline manually for each such chunk is hard and time-consuming. Whether users could simply point us to a target table that demonstrates how the output should look like. For example, users can point us to an existing database or point us to a visualization, which are very easy for users to specify. This is an entirely new problem formulation not being studied before because unlike a query by output and SQL by example that requires a matching pair of input-output table, we use a pair of input-output tables that do not need to match, which is a lot easier for users to provide. In our by-target synthesis, we consider the following two types of operators: string transformation and table reshaping. We're given as input a few files as well as a target output table. Our goal is to produce a synthesized pipeline using these operators to generate a result table that looks like the given target. Now let's talk about how such a system can be built and evaluated. We built upon a prior work that crawled and replayed millions of Jupyter notebooks from GitHub, which are essentially data pipelines. And we use these real pipelines as our test bed, both for our algorithm to learn from and to evaluate against. Now, because by-target is a fuzzy specification, let's first talk about how we use real pipelines to evaluate such a system. So for each pipeline, we split the input table used by the pipeline into 50-50 of testing and training. And we treat the first 50 as the first batch and use the ground truth pipeline L authored by humans to generate the target output. We then use the remaining 50% as a new batch, and together with the target, we will synthesize a new pipeline L hat. The correctness of the synthesized L hat can then be verified on the first 50% of the data by checking whether the results from the original pipeline L and new pipeline L hat are identical. Now, some of you may wonder whether by-target provides a sufficient specification of the desired pipeline. Our key insight is that we can leverage implicit constraints like keys and FDs. Let me show you using a simplified data pipeline from GitHub for a Kaggle challenge called Titanic. In this task, the goal is to predict which passengers survived using the feature like gender, fear class, and etc. A common pipeline in this case would form a GroupBy on the gender column to compute average survived by gender, and then a join on gender to bring the average survived into the original input as an additional feature. Our insight is that such cases, the desired pipeline can be uniquely determined. Specifically, we can discover two constraints in this case, a key column passenger and functional dependency gender to average survived. Now, assuming a new batch of input arrives with different passengers, in order to synthesize an output table with the same setup at KFD constraints, the smallest pipeline is to exactly group by on gender and then self-join. That uniquely determines the desired pipeline using a fuzzy target alone. With this intuition, we now formalize this problem. We're given a bunch of input tables and target tables, and also a set of operators we can invoke. We synthesize a pipeline L using the following optimization problem. Let's first talk about the constraints. Like discussed before, we want our synthesized pipelines to have the same constraints like the one in the target table. This includes K and FD constraints. We also want the columns in the target table to map to our synthesized output. And our objective function is to maximize the joint probability of the operator in the synthesized pipeline. We infer such a probability using a framework called auto-suggest. Intuitively, we want to find a most likely pipeline, satisfying all these implicit constraints. Given the formulation, we're now ready to describe two algorithms we propose. One is based on search, another is based on reinforcement learning. For the search-based method, we use a beam search, which keeps the k-promising partial pipelines for all pipelines of depth D, and the D equals 1, 2, and etc. Among these key partial pipelines, we consider a balanced set of criteria, like keeping K over 3 promising pipelines based on the criteria that corresponds to our objective function and constraints used in our optimization problems, which are FD key, column mapping, and operator probability. In addition to search-based heuristics, we also propose our RL-based search algorithm inspired by game playing, like AlphaGo, where RL agents can learn to play via self-play. We use RL in a similar manner and train an agent to synthesize pipelines using what we call self-synthesis. Specifically, we model each node in our search graph as a state, which corresponds to a partial pipeline, and the transition of adding a next operator into a partial pipeline as an action. We then give an RL agent large number of real pipelines and ask it to synthesize itself and reward the agent when it succeeds. We now briefly discuss our experiment results. Because by-target is a new paradigm not studied before, we compare auto pipeline with methods from the by-example literature, such as SQL by example. We also compare with tools that leverage context and auto-suggest, which is a recent approach we leverage that automates single pipeline steps. For our proposed auto pipeline, we include 3 variants: the diversity-based search algorithm, unsupervised learning-based method, and the RL-based approach. We compare the success rates of synthesis across different methods. The x-axis shows the accuracy, and the figure shows the average accuracy over 700 real pipelines. As we can clearly see, auto pipeline-based methods can consistently synthesize over 70% of the pipelines from this benchmark, which is substantially more effective than other methods. More experiments can be found in the paper. There are many additional experiments we perform, such as error analysis, robustic analysis. That is it. Thank you for listening, and I'm happy to take any questions.